Hello, everybody. You are welcome to part 5, clip 1 in part 5. Actually, there has been minor change here. This part was also included as a different section in part 4. But after that, I have decided to separate it as a different part because the topic seems that a little bit different than the performance and requirement which was covered in part 4. But here in part 5, we start with modern modulation techniques, which can be like different topic. So, um, so this is clip 1 of part 5, and in this part, we are going to discuss some of the modern multiple access and modulation techniques like code division multiple access, orthogonal frequency division multiplexing, space-time frequency coding, non-orthogonal multiple access, and radio receivers, software-defined radio. The learning outcome of this part that after watching carefully and studying the recorded clips of part 5, this should be part 5, and attending the online sessions and performing the quizzes successfully, you will be aware of the most advanced modulation and multiple access technologies like CDMA. Actually, today in this clip we are going to discuss direct sequence, frequency hopping, and time hopping CDMA. And next clip we were talking about the orthogonal frequency division multiplexing and non-orthogonal multiple access. So, and also you will be aware of the structures of radio receivers in general and the recent, not recent actually, this is the recent development of the software defined radio SDR. So this is the learning outcome of this part 5. Actually, in modern telecommunication system, we are aiming to have a very efficient multiple access as well as modulation. And efficient means it has different dimensions when we say efficient system. So it can be in spectrum. So we need to have like a very high usage of the spectrum, which is given as the spectrum efficiency, where we mentioned that it is bit per second per hertz. So we are looking for the multiple access or the modulation which can achieve the highest possible efficient use of the spectrum. Also, we mean the complexity level. So we are not looking for a technique which require a lot of algorithms or complicated algorithms, which means that it needs, for example, a lot of iterations and very high computational cost, because this can be like complicate the receiver, and not only the complication in terms of integrated circuit or right now we have like very advanced VLSI system, that which means that we can generate very high efficient like computing devices. But the problem that we will need a high computation power. Computation power means that it will drain the battery of the mobile phone or of the receiver very fast. So we are looking for to the light algorithms, and it can also handle the problem. The size, for example, of the antennas required, and actually many different dimensions that we need to look to during the design of modern communication system. We mentioned in part 3, when we talk about wireless channel, different kind of problems in wireless channels like fading, and we talk about frequency selective fading or flat fading, or on the other side, when we talk about the variance of time in the channel, we talk about fast fading or slow fading, and we have shadowing and so on, and destructive fading, for example, and such kind of problems that they will limit the data rate or the symbol rate or the speed of the and also the reliability of wireless communication. So the new multiple access or modulation techniques we are looking for, that they should handle or mitigate such kind of problems. We mentioned before that even if you have wide like bandwidth, if I, for example, you got 5 megahertz of bandwidth, sometimes if you don't use some advanced modulation technique, so the ISI might limit your usage of that bandwidth. Even you have 5 mega hertz, which means that even with the slowest like speed, which means that 1 bit per second per hertz is that 5 megabit per second. Sometimes you are not able even to achieve this 5 megabit per second because of this ISI. Especially that when we have like the spirit delay, certain spirit delay, or certain characteristics of that channel, it might limit the usage of that spectrum to be very much lower than this 5 megahertz or 5 megabit per second. So this actually makes the communication not efficient at all. So what we're looking for some smart way of multiple access or for modulation that it will mitigate or solve the problems of this ISI, for example, or fading, or mitigate them at least. So most of the modern communication systems actually are based nowadays on either code division multiple access CDMA, orthogonal frequency multiple access, or division multiplexing. We will see the difference between them later, and the non-orthogonal multiple access. Actually, the CDMA, it was the core of the 3G network, the UMTS network 3G. So it was this wide band CDMA. Also, it was used before, like in IS-95. It is called CDMA 1. It has been also used in other short range communication like Zigbee, and also nowadays it is one of the used multiple access techniques in new technologies like long range wide area networks. So CDMA is one of the strong actually candidate, and it has been already applied in many of those technologies. So CDMA is one of the powerful technique which can handle many of the limitations of the channel. Also, we have the orthogonal frequency division multiplexing. Actually, this OFDM or OFDMA has been replacing CDMA in many new technologies. Actually, for example, in Wi-Fi, if I remember well, only 802 11B is using CDMA. The others, most of the others use OFDM. And also LTE advanced and 4G is based on OFDM. um, Many other like short range and wide range technologies are based on OFDM. So OFDM, it has many like features over CDMA. Because of that, they were like implemented in many technologies, communication technologies. And maybe the major benefit of OFDM that it has like a simpler receiver architecture than the CDMA. Also, in 5G and in a new radio, they have start using the non-orthogonal multiple access. So it is called NOMA, and we will see the difference between them. But let us in this part 5 start to review all these technologies. So after watching these lectures, so you will be aware about the difference between them and the concept and the major concept of each of these technologies. I want to mention one important point here, that in this part we are using to use math. So we didn't, or I tried actually to avoid as much as I can mathematics in the and algorithms in the previous parts, and also in the coming parts. So I will reduce the math as much as I can. But in this part 5, we will see some algorithms, some mathematical equations. And if you don't have enough background to understand what I am saying when I am talking about certain equations, so just listen to them but ignore these parts. So, however, that for those who have some background in mathematics and or they studied these things before and they want to review the concepts here, it would be beneficial for them to follow me in that math description. Okay, in this clip one, I will start with code division multiple access, or it is known as the CDMA. Okay, the CDMA usually utilizes what is known as spread spectrum techniques. So the main idea of the spread spectrum techniques is to spread the original signal in a frequency domain using another signal, which can be independent to the information signal. So we have two signals: the information signal and the spreading signal. So the spreading signal, it will spread the original signal into much wider bandwidth. For many reasons, several modern communication systems use code division multiple access, which is one of the spread spectrum techniques, as I mentioned just now. So this is the idea. Actually, the idea is based on that if we have different users, as you can see them here, so I use some orthogonal codes: code 1, code 2, code 3. So ideally those codes should be orthogonal, which means that if you take the integration or the cross correlation between them, the result will be 0 and the autocorrelation will be 1. This is called orthonormal codes. Okay, I am coming to describe this in more details. However, because of the multipath and delay of the channel, so even if they are orthogonal at the transmitter, you cannot guarantee that they will be orthogonal at the receiver. So the idea is that we keep or we use codes that even if there is some delay in that codes or in those codes, the cross correlation will be small as possible. It is not 0, but it can be very small compared with the autocorrelation of the code with itself. Okay, so in that sense, we use those multiple codes: code 1, code 2, code 3, because actually when we relax the orthogonality condition in the transmitter, then we can use more codes. So we will have more codes to be used. But if we concentrate that they must be orthogonal, so the number of orthogonal codes can be small. Okay, now we transmit this signal, as you can see that over the channel, over the same channel, and for each receiver, they will use its own code, as we will describe later, to demodulate or to detect the transmitted information. This is the transmitted information from user 1, from user 2, and from user 3. There are many benefits of using CDMA. So if we read together with them, so it is not needed to divide the time resources. So for example, in time division multiple access, we need to have time division. So we have to divide the time between users. And that need, in that sense, we need synchronization between transmitters and receivers. Here, we don't need to divide the time resources because all of users can send in the same resources. Of course, there is also time-based CDMA. There's another thing, okay? But here now we assume that the basic CDMA, so we don't have like time division or time scheduling in this system, so we don't have to divide the time resources, and also the frequency, all frequency will be available over all users. Okay, of course the signal will be widely spread, so it will use more bandwidth than the information itself, but still we will see the benefits of that. Uh, yes, so it doesn't need very accurate timing, as we mentioned. It has smooth capacity. I will explain what smooth capacity means in more details when we come to the mathematics of CDMA. But here, the nice thing within the CDMA, you can control the quality of service without radio replanning the radio system. For example, if you have a system like GSM based on the frequency division multiple access and time division multiple access, and you need to for example to increase the number of users within cell, or increase or decrease them, or increase the quality of service of some users, usually you will need to do some changes in the size of the cell, for example, or the transmission power, of the base station, or maybe the antenna, or height, or sometimes you need also to increase sectors, for example. So it is not that easy to do it. Here in CDMA it is much easier, because you can control the quality based on the spreading factor, as we will see them later. So we will come to this in more details. It has wide bandwidth, which offers frequency diversity. So because the signal, it will be spread over frequency. So if there is some corruption or some like drop in part of the band of that signal, you still be able to recover the signal. Also, it provides some kind of time diversity when you use rake receiver. I explained this before when we talk about diversity. So rake receiver can provide some kind of time diversity, because it can recover also the multi-paths. So when you have some delayed path, you can still recover the signal by using the rake receiver. So if you lost or the signal noise ratio for the one path was not enough, then by using a rake receiver you can accumulate the signal to noise ratios from all paths. The split spectrum signal has security nature, because it couldn't or it could be difficult to detect it, because it has wide frequency. So it means that you distribute your power distributed over wider frequency, which means that the energy, it will be very small. So it will be very hard to detect the signal. Sometimes it can be very close to the noise floor. So sometimes even it is not possible to detect that there is transmission here, especially when you have like single transmitter. Of course, if you have many transmitters, all of them, the CDMA, the power can be accumulated so that it will be detected. Um, Also, the space spectrum, it has wide bandwidth, which means that it will be much less affected by the fast fading nature of the channel. And also the signal can be spread and dispersed using relatively simple circuits. So the concept of transmission, or the concept of modulation and demodulation, is very easy to be done in CDMA. But of course, if you want to take into account the multipaths, the rake receivers, and so on, so the things can be difficult in that case. So what is the idea? The idea of the CDMA, that assume that this is the information bits that you have. You have binary bits like 1 and 0. Here we use non-return to 0, which means that 1 is represented by 1 and 0 is represented by -1. Okay, so in that case we have like 1 and -1 and 1. Okay, if you multiply, just simple multiplication of this signal with the coded signal, uh, usually we call it like BN, like pseudo noise, okay, or pseudo random signal. So when we multiply them in this random code, it is random for others, it is not random for us. We generate it, so we know it. The transmitter knows, and also the receiver knows the code. But for the others, it should be random. So for them, it is random, and it cannot be. It is not. It is unknown. Okay. So when you make the multiplication, what happens? If you just concentrate in this figure, so you can see that this part is multiplied by what? By 1. So when you multiply anything by 1, it will be the same. Okay, this second part will be multiplied by -1. Anything multiplied by -1 will be what? Reverse it. So if this is 1, it becomes -1. If it is -1, it becomes 1. That's it. Okay, so it is just multiplication with none return to zero, a binary data of the user multiplied by none returning to zero, the coded signal. So we got the B in sequence. Now, this B in sequence is spreading the original signal. Okay, how can you get back the information signal? This is at the receiver. Simply, at the receiver, you will multiply this B in sequence by the same code. When you multiply it by the same code, 1 times 1 is 1. Minus 1 times minus 1 is 1. 1 times 1 is 1. 1 minus times 1 is 1, and so on. So if the transmitted information was 1, it means that both codes will be identical, and when you multiply them, it will generate 1. The other part of the signal, which is minus 1, here the code is reverse of the original code. So when you multiply them, they will generate minus 1. Actually, very simply, that in the transmitter case or the modulation case, sorry, if we have this is information signal x of t, okay, simply we multiply them by the code. Then we generate this signal. In the receiver side, what we do, for example, if this is the result is y of t, if we have here y of t, simply we multiply it by the same code, then we will generate x of t. It is very easy. I mean, the modulation and demodulation are extremely easy in this CDMA system. But of course, when we realize this in reality, it will not be that nice way. There are many actually problems here, as you know that the code that it is received here, it will be delayed, and this delay time can be random delay. So we need to use some estimation of the delay in order to generate the code, because the code here is received. We don't know when the code starts exactly. So what happened now? We need at the receiver to track this delay, the channel paths, in order to generate the code with the right starting time or with the right phase. Okay, and in that case, if we use the same code, but this code was delayed, there is delay, or there is big delay, more than one chip, then we might lose the signal. We might get wrong result. So we need always to have, or we have some problems also associated with CDMA, and it is expected, of course, to have such kind of problems. But if we want to build transmitter and receiver, for example, with like over wire line, and the delay is fixed, so the transmitter and receiver can be very easy to be implemented. Okay, this is of course the data of the user. We call it as bit, but this bit of the code we call it chip. Okay, we call it as chip. So we call this as chip rate, and we call this as bit rate. Okay, this should be clear. Yes. So this is the concept of transmission. And what is if you want to use 0 and 1, not 1 and minus 1. So actually, in case that you use 0 and 1, you use XOR instead of the multiplication. Why? Because look to this. If you have this XOR and we have here A and B. Okay. Look what happened if A is 0, because this is the truth table of the XOR: 0 0 0 0 1 1 1 0 1 1 1 0. This is called also module 2 summation. Okay, now if one of the inputs is 0 0 0, and the other input, when the other input is 0, it will not change, it will be 0. If the other input is 1, it will not be changed, it will be also 1. So if A is 0, the other input will not be changing, it will be the same. But if A is 1, if the other input is 0, it will be 1. If it is 1, it will be 0. So it is reversed. Okay, It is the same as the multiplication that we said when non-return to zero modulation. But here, if we have return to zero, which means that the data is one and zero, then simply we use XOR. It will do the same job as done by the multiplier. So we have here our information at A. So this is bit 1 and bit 0. So the bit time is TB. Then in the other input, we put the code, and the code is some code that, as I said, it is B in sequence, pseudo random or pseudo noise. And then it has, for example, you can see that it is 0, 1, 0, 0, 1, 0, 1, and so on. So when the input is 1, then this will be reversed. If the input is 0, then it will be the same, as you can see in the result here. Okay, the chip rate is 1 over TC. TC is the duration of one chip, and TB is the duration of one bit. So FB is the bit rate, FC is the chip rate. Okay, in the receiver side, it is exactly as the multiplication, as we saw in the multiplication. If we use the same code in the receiver side, then we can regenerate the transmitted signal again. Okay, now even if we have multiple transmitters on the same channel, but all those codes are orthogonal, which means that the result will be only for our transmitter where we used it is on code in the despreading process or the demodulation process. Here we have very important parameter. It is called the processing gain. The processing gain is given as the chip rate divided by the bit rate, or the time bit, the duration of one bit divided by the duration of one chip. So this gives you the indication that how much the original signal was spread in the frequency. Sometimes they call it spreading factor, not processing gain, but spreading factor. It is actually quite similar, each one. So spreading factor or processing gain, those are a key factor in the performance analysis on CDMA systems, as we will see them soon. So you can see here in this figure, for example, you can see that when we have the information data, this is the information. We assume that it has this power spectral density limited at PB, okay, and this is the code, the pseudo-random code. It is called pseudo-random BN or pseudo noise, because it has almost like the same white noise as the additive noise. So it is white like in this way, but of course it will not continue to infinity, but up to BC. What is BC? BC is related, or you can actually say that is equal to 1 over the chip rate of the code. Okay, or related. It is related. Okay, so now what happened when you make this multiplication? If we have non-return to zero, or we use XOR gate, if we have return to zero, what will happen? That this data, this information will take the same power spectral density, or similar to the power spectral density of the spreading code. So it will be like this one. You can see, yeah. So now you can see that we have maybe strong jamming here. This one, this is in the transmission, the voice channel. This is the additive white noise. This is in the red color, which is very close to the spread of our data. We might have interference, as you can see here. So at the receiver side, what we are doing at the receiver, what we did when we use that demodulation, we call it despreading. Despreading, it means that we take the spread signal after the split spectrum, and we bring them again to the same band, that of our information. Okay, what will happen for the strong jamming or for the interference? Actually, the strong jamming is only jam part of the frequency. So even if this part was like corrupted, but still this part will carry very little information of our data. So we can correct this error by using the forward error correction, for example. And also for the interference, if there is interference, they use, for example, also another spread spectrum. Then when you make the despread of our original signal, the other signal, it might also spread again. So you can see that its power spectral density will go even lower, smaller, and the jamming will go also smaller compared with our original signal. So CDMA has high immunity against jamming and against interference when they send in the same like spectrum technique. So this is some of the benefits of using the code division multiple access. Okay. Um, okay. Now we have this system. So you can see that we have some simple modulation and demodulation, as you can see. So in the transmitter, we have the bit. We assume that we have transmitter I, and this is the information that we want to transmit, and we multiply it. We assume here none return to zero. We multiply it with the code I. Then we have digital modulation. For example, I assume it in this mathematical analysis binary phase shift keying. Okay, and then we transmit the signal will be received over multiple paths, but also we might have other interference using the same CDMA, and maybe we have also noise, and many different signals will be received at the receiver side. So this is our receiver side, where we have digital demodulation for the binary phase shift keying, so we can use multiply it again by cosine 2 by FCT as we saw before. So now this is the receiver of I. After that, we use of course low pass filter, and then we multiply it by the same code again, and then we use the correlator or the detector in the output. Then we got the bit of the bit number j. This is the jth bit. So here bj means that bit number j of user I, comma I means that for user I put here hat because this actually is not only the transmitted bit, this is b J, okay, not only the transmit bit, but also can be corrupted by the multipath, by the ISI, by the other interference signals. So let us see mathematically how will be the received signal, and mathematically let us follow step by step what happened from that transmission up to the reception. This will clarify the benefits of using direct sequence CDMA, and we will understand them in much more like details and deep enough to see after that the other systems and to be able to compare between them. Let us stop here for clip 1 in this part, and we continue in clip 2. Thank you.